Good evening, everyone, and I would like to thank the organizers for giving me the opportunity of presenting my work. I'm Nicola Principi, first year PhD student in Warsaw, and today I will be talking to you about cross correlations between CMB, and I need this, and large-scale structure with our set of simulations, Teresita. So I will start with a brief introduction on CMB lensing, then I will go on talking about the large-scale structure part of our simulation. Then I will tackle the CM part, CMB, and then I will give my conclusions and talk about some future prospects. Let's start with the introduction. So we're talking about CMB lensing, which is the deflection of CMB photons by large-scale structure. It falls into the weak lensing regime. And let's say one of the most important features of this effect is that it is an integrated effect. So it's a cumulative effect. We can compute the lensing potential here. The lensing potential can be computed with this integral on the top right. And we see that this is basically an integration of the gravitational potential psi. And the effect that CMB lensing has on the temperature or polarization maps is basically a remapping. So the field, delta T tilde, gets remapped in a field which is shifted by this gradient of phi, which is it's called a deflection field. So this is the effect, and it's very important to reconstruct. First of all, because on one hand, it is a tracer of matter distribution. We can study cross correlations of CMB and galaxy catalogs in this way. And it's also important because it allows delensing. We can use algorithms to remove the lensing effect from CMB, and so we can clean the CMB maps and have better constraints on the cosmological parameters, especially for the B mode power spectrum, which is highly affected by lensing effects. The research direction right now is one of using quadratic estimators, such as the ones proposed by Juan Okamoto in 2001, to reconstruct the lensing potential for this, and implementing more and more efficient delensing algorithms, and also studying, as I said, cross correlations of lensing kernel with tracers to allow the tracing of the dark matter clustering. All of this obviously aims to improve the constraints on cosmological parameters, especially as I said, with the B modes power spectrum, from which we can get very important information on the tensor to scalar ratio. And for further information on this, please refer to Kish and Deka's talk in a couple of days. And with Teresita, which is the tomographic ensemble of realistic simulations of tracers and anisotropies, we want to offer a tool to tackle these new issues. So it's a set of 50, soon at least 100 simulations, each one including an LSST-like galaxy catalog, having both true and photometric redshift from redshift 0 to 3, a convergence map, which is the ablation of the lensing potential I was mentioning before, correlated with the catalog, and unlensed CMB realization, which might come in handy, and temperature Q and U polarization maps lensed with the convergence map obtained from the galaxy catalog. For 6 different frequency channels, we use the specific of CMBS4. Let's now talk about the large-scale structure part. We use GLASS, the generator of large-scale structure, which works on shells. So basically, it's random realization of log-normal fields, and giving some input fiducial power spectra. This code is able to generate overdensity fields or convergence fields, which might or might not be correlated. It depends on if you provide also the cross correlation spectra. We use eight shells, one for each tomographic beam, plus one, which is the convergence shell. So we use 9 shells we have a total of 45 input power spectra. And as you can see in the bottom right, maybe it's a bit little, but in the central part you have galaxy-galaxy cross correlations, which are assumed to be zero, of course, in the case of true redshift. And the fiducial power spectra are computed with the limit approximation here in equation 1, with obviously different kernels for convergence and galaxy power spectra. And here on the top right, you can see what an overdensity map looks like in an LSST-like catalog. While we decided to store the catalogs only in 2000 square degrees for time reasons mainly. But I mean, results, LSST-like results can be obtained just with simple rescaling of the fraction of the sky. And here on the left, you can see the n of z of the different tomographic bins from the Rayleigh distribution, which is the LSST distribution, and the lensing kernel of the CMB. So you can see, obviously, CMB and galaxies are always cross-correlated, while galaxies are not correlated between different bins. If we add the photometric errors, then these separations are not so net, and they will overlap a bit, and you will lose some power in the outer spectra in favor of some power in the cross spectra. This is a close-up of the catalogs. And as you can see, we have the first shell for the convergence, and then 8 galaxy beams, so you can see how the overdensity map evolve through the tomographic bins. Of course, we can compute our power spectra from the catalog, and we can see that, it agrees with the theoretical one. As you can see, also the cross spectra between galaxies are consistent with 0. And on the left, you can see the comparison between the Rayleigh n of z, so LSST simulation, and our catalogs, so true redshift and photometric redshift here in yellow, showing that the photometric one obviously is a bit more smoothed. Now let's talk about the CMB part. We just generated, first of all, a lensed CMB realizations with classic ELPi, so from just a Gaussian distribution, and then we lensed those CMB realization with lens peaks, and using the convergence from the large-scale structure simulations. So we have galaxy catalog, from that convergence correlated with galaxy catalog, and with that convergence we lensed the CMB. And so we this way we aim to achieve a realistic CMB observation. Now in the bottom line you can see the difference, lens minus unlensed. This is the effect of the lensing basically. Now it's difficult to see it from this slide, but the next two give an idea of what happened, this remapping of the fields. And in this slide, you can appreciate the correlations between the different quantities. So here we have phi, the lensing potential, which is correlated obviously with its divergence, the psi. This is phi, sorry. This is called the deflection field, as I was saying before. And here you can find the difference between lensed and unlensed for both temperature and polarization. And you can see that the 4 images are highly correlated. Just by eye, this just right band here, or this spot in the bottom left. And in the end, of course, you can retrieve the final power spectrum from the simulations, and you can see that we are consistent with the theoretical one, well within the cosmic variance. We did it for 6 frequency channels, as I said. You can see like following CMBS for the CMBS for science book. And each frequency channel obviously has its resolution and a different kind of noise. This is for 150 gigahertz. So in the end, what did we do? We built this set of simulations They consist in galaxy catalog, convergence correlated with galaxy catalog, and the CMB observations lensed by the convergence. And we believe that this set of simulation would be a useful tool for many things, like, for example, testing the lensing algorithms, which is the next step in our timetable, let's say. You can study cross correlations between traces and CMB, so being the matter distribution. You can study the effect of photometric errors in the LSST survey or other photometric survey if you choose to use other specifics for the galaxy catalogs. And obviously the simulations will be improved. They are just born, let's say, and we will add the foregrounds, both galactic and extragalactic foreground, to make it even more realistic. And you can also simulate using fiducial power spectra that do not assume a standard lambda CDM model, but maybe using some different dark energy models, so to predict what effect would it have on the CMB observations. And they will be soon available, so I hope it will be useful not only for me and my group, but also for other people that want to do something with CMB and cross correlations with galaxy catalogs. And thank you for the attention.
Questions? Yeah, David.
Yeah, so thanks for the nice talk. So maybe you mentioned this already, but when you mention LSST like simulation, is it the same as the Cosmo DC2 sim, or is a different one?
It's the rail simulation, which is rail, R-A-I-L.
Yeah, this is the name for the photo set for the redshift, or is also so from rail is taking the whole sim or just the photo set?
No, it's taking the NFZ.
Right.
To use it as like an input for our simulations that are much let's say much quicker and stuff, because obviously they're mostly angular simulations.
All right, I see. Thank you.
There's a
I
question
think
on Zoom. Yeah. Okay. Yes,
So you
I
can unmute
get that.
yourself, like, I think, hi, you can unmute yourself, I hope.
I was not considering the Zoom
Uh,
audience.
so like, he should unmute himself, yes?
Sorry, can you hear?
Yes.
Okay, great. Yeah.
Not very loud. Uh, yeah, we can hear you.
Okay. Right. Yeah, thanks so much for the talk. It's super great. Really exciting. I want to ask you, are these mocks like ready? And if not, what's the rough timeline and would they be made like public?
Yeah, thank you for the question. Actually, this is they are, yes, like 50 of them are ready, and we are going to reach at least 100 like in a couple of weeks, just the time of running the codes. Yeah, and they are not public available yet, but we plan to make them public available. And so I mean, maybe you can have my contact information, and I can just like book you when when they will be available. And maybe I can write something on the Zoom chat. Yeah.
Okay. Then, if there are no more questions, thank Nicola again.